In the last video, we had a look at a couple of examples where we used differentiation in physics. But there are examples where the rule we saw isn't going to be much use. This is the rule we looked at, and it works for polynomials, but doesn't work for things like trig functions. It's possible to figure out how to differentiate the most basic trig functions, that's sines and cosines, by intuition if you remember what differentiation is. Differentiation is how we figure out what the gradient is of the tangent at every point on a graph. So let's consider this first case, where the function of the x-axis, and the x-axis is theta in this case, is sine theta. Here I'm measuring theta in degrees. And you can see this point here is 180 degrees, this point here is 360 degrees, and so on. This is minus 180, and so on. Now, if you have a look what's happening to the gradient of the line, that's the interesting thing. And we're going to take some points along this graph. We're going to start here, then we're going to look here, then we're going to look here, then we're going to look here, and then we're going to look here again. And then the whole function keeps repeating. Let's call this point A, let's call this point B, point C, point D, and point E, which is the same as point A. Now, to take point A, we have the absolute maximum value of the gradient. That's the point where the line is steepest and positive. So d by d theta of sine theta is positive, and it's at the maximum value at point A. At point B, the gradient is now 0. If you drew a tangent at point B, it would have 0 gradient. At point C, we now have the maximum value gradient again, but it's negative. So I put a minus sign in here. At point D, it's 0 again. And at point E, we're back to the same value we had for point A. And the whole thing repeats. Now, I've put a little note down here at the bottom here, which I think is important. If we were using radians, and I know we're not, but if we were using radians, for small angles, sine theta would equal theta. And if you don't believe me, grab your calculator and try it out. For very small angles in radians, sine theta equals theta. This line has a gradient of 1 through the origin. So d sine theta by d theta, that's the gradient of this line, through the origin would look like d theta by d theta, which would be 1. Now, actually, this shows why we tend to use radians more in calculus and in some of the more advanced physics, because of this statement. And obviously with calculus, where we're looking at very small changes, this statement becomes very important. But it doesn't matter. We can use this idea of theta in radians and always convert to degrees later to plot a nice pretty graph if we want to. The shape of the graph is the same, regardless of whether we use degrees or radians. It's just the values on the x-axis change. We're going to use this small angle approximation that says that theta gets closer and closer to sine theta as theta approaches 0 to find the gradient of the line at point A. Because d sine theta by d theta becomes d theta by d theta. Dividing anything by itself is just 1. So the gradient of the line through the origin here is 1. So this maximum value is 1. And that means this maximum value down here is 1 as well. And this maximum value here, well, it's minus the maximum. Well, you can see this whole function is symmetrical around point B, so this would be minus 1. Differentiating this function, sine theta, we should get a function that has a value when theta equals 0 of 1. A value when theta equals, well, in this case it's 90 degrees, because we're working in degrees, is 0. A value when theta equals 180 degrees of minus 1. A value when theta equals 270 degrees of 0. And a value when theta equals 360 degrees back to 1 again. And this function should keep repeating. And we know a trig function that passes through all those points. So you can see here at point A, we needed the value 1. We've got the value 1. At point B, we needed the value 0. We've got the value 0. At point C, we needed the value minus 1. We've got minus 1, and so on. So the function that gives us these values is a cosine function. The first derivative of a sine function is a cosine function. So what's the first derivative of a cosine function then? Well, let's look at those same 5 points. A, B, C, D, and E. Point A and point C and point E, you can see that the gradient of the tangent at those points is equal to 0. Point B and point D, you can see it's a negative gradient at B and a positive gradient at 1. And you can see because the phase difference between point A and point E is 360 degrees, which is the same as we had last time, and we are passing through the same points, the same spacings, then we're going to have the same magnitudes of 1 and -1, -1 here and 1 here. You can see that by inspection. The gradient of this line, the magnitude of the gradient of this line and this line were the same as we had last time. The sine theta graph went from 1 to -1 and had a phase difference from one peak to the next of 360. This graph goes from 1 to -1 and has a phase difference of 360. It's just everything shifted. But it means the gradient at B and D are going to have the same magnitude as the gradient at A, C, and E in the previous example. So at B it's -1, and at D it's 1. You can see that by inspection, by just looking at the graph. So now we need a trig function that has a value of 0 when the angle is 0, a value of 0 when the angle is 180 degrees, a value of 0 when the angle is 360 degrees, but then takes a value of -1 when the angle is 90 degrees, and a value of +1 when the angle is 270 degrees. Well, we have a function that does that as well. You can see at point A, the value is 0. At point B, the value is -1. At point C, the value is 0. At point D, the value is +1. At point E, the value is 0. Exactly as we should get. And this function is a minus sine theta function. So the first derivative of a cosine function is a minus sine function. Well, let's finish off. Let's differentiate this minus sine function and see what we get. Here are the gradients of the tangents at those 5 points we've labelled on the diagram. And just as before, because the function extends from 1 to -1 with a phase difference of 360 degrees, it's the same shape graph, it's just been shifted. We know the magnitudes of these gradients. -1, 1, 0, 0, -1. So here they are. And do we know a function that has these values at these points? Well, yes, we do. A minus cosine theta function will fit those criteria. -1 at A, -1 at E, 0 at B and D, and 1 at C, just as you can see here. This means that the first derivative of a minus sine theta function is minus cosine theta. Now, when writing it, put some brackets in here. Otherwise, this looks like d by d theta subtract sine theta. I'm not really sure what that would mean. So put some brackets in there. So we'll just finish this off now then. So at point A of this minus cosine theta function, the tangent would have a gradient of 0, as it would at C, as it would at E. At B, that gradient would be 1, and at D, that gradient would be -1. Do we have a trig function that has those values? Yes, we do. That trig function is a sine function. So value of 0 at A, a value of 0 at C, a value of 0 at E, a value of +1 at B, and a value of -1 at D. Exactly what we should have. And we're back where we started. We could keep differentiating and keep going around this loop. Now you can find differentiation of trig functions all over the place in physics, from simple harmonic motion to electromagnetism. And we're going to have a little look at those examples in the next video.